right, hi stats people. This is 3.1 notes. So in this chapter, we're going to start looking, instead of just at one variable, we're going to be looking at two variables. So we're going to have names for them. We're going to have a response variable, and then we're going to have an explanatory variable. And that's really just another way to say that we have an X and a Y chart. Okay, so we're going to basically be doing an X and a Y. Okay, so which one is which? Well, the one that has an X in it is the X variable, and the other one is the Y, or you can think about it in terms of alphabetical. E is before R. And we've already done some practice on some of these earlier in the year when we had you label things as EV or RV, right? I believe we did that already. All right, so when would I use two variables? Well, maybe I'm interested in finding out, if we would have been in school, we would have been doing a starburst activity. And we would have been trying to figure out if there's a relationship between the size of my hand and how many starbursts I could pick out of a bowl using just one hand. So I'm going to write that down as a question. I wonder if the size of my hand influences the number of starbursts I can pick up. Now, if you want to tell your parents that you need starbursts to test out this theory, feel free, but we're gonna skip that until I see you in person. Okay? So notice that just because there is a relationship, it doesn't mean that one causes the other. And so we want to be careful about using the word cause in two variables. We want to be talking about relationships between the two variables, but not that one causes the other. Okay? Sometimes we can make that happen, but most of the time we're just talking about an association between those two things. Okay, so we're going to create a scatter plot. Scatter plot is just your usual graph, a coordinate plane, except for stats we usually tend to stay in the positive zone, so in quadrant 1. And it's the relationship between two quantitative variables. This is really important. Quantitative means they have to be number type of variables. You can't be doing this by color of starbursts, right? They have to actually be points that you can plot. Okay, so I want you to think about that as points that I could plot. So if it is not a coordinate point, I should finish that plot. I could plot. So if it is not a coordinate point, it is probably not two quantitative variables. Okay? So usually on the horizontal axis is our explanatory variable, on our y-axis is our response variable, and each individual combo of those would turn into 1 point on the graph. So how do we go through actually making a graph? Well, fairly simple of how you would do any other graph, I suppose, is the first thing you'd have to decide is what goes on X and Y axis. Okay, remember that in the x-axis, this is usually your explanatory variable, and your y is usually your response variable. Right? So in my case, I'm curious about the explanatory variable, the size of my hand, the length of my hand from my palm of my hand all the way out to my longest finger. Is that related to how many starbursts I pick up? Right? It's not like, is the number of starbursts related to how long my hand is? I'm really trying to determine if I start out with a bigger hand, am I going to get more? Or if I start out with a smaller hand, am I going to get less? Okay, so that's what we're thinking about there. So next thing is we want to label the X and Y axis, plural is axes, with good labels. So that means numbers and labels. And don't forget to do good number pacing and spacing, evenly spaced. Okay, so evenly spaced markers on the X and the Y axis. And then lastly, if we want to do the plotting, that's going to be plotting the individual points. All right, so when we are done, we typically have a graph that looks like this, and it has a few points on it, depending on how many data points, how many people are in our class, might determine how many points we end up on this graph of the X and the Y axis. where the x might be the length of hand, and the y would be the number of candies. Okay? All right, let's say they already gave us this graph and they want us to describe it. So remember that before we were using socks, right? Well, in a two-dimensional, when it's got an x and a y, we need to use direction, form, strength, and outliers, okay? So I have yet to find a really, really good one for this one, a good word to remember this one. I've heard other teachers will use the word duffs, so they'll call this D-U-F-S, duffs, okay? From, I should spell that the right way just so they can see it, duffs. Kind of like from The Simpsons, right? That they have a factory there for a product called Duff's, right? So kind of that. Okay, so let's go through and talk about what each one of those is. So the first thing you would want to do is you'd want to say the direction. And really this is just another word for slope, right? You want to say that it's positive, negative, or neither. So are those points kind of moving in the x direction and the y direction that they're both positive? Are they, as the x's go up, are the y's going down? That's negative. Or are they kind of all over the place and so it kind of looks flat or you can't tell which way the general trend is? So direction is either positive, negative, or neither. All right, next one is form. Does it look like there might be a best fit line to suit this data? Or does it more look like a curve, like maybe a parabola or a sine curve or something like that? Our main focus for AP Stats is usually linear, but you should know that there are other patterns out there that would use other methods as well. Okay. All right, next one is, let's take a look at strength. So we've got strong, weak, or moderate. So a strong strength would be points that are basically make the line up already. That would be a strong one. A weak one would be one kind of like this where it's kind of hard to see the line. You can kind of fit it in. And moderate would be somewhere in between there. So weak is, it's really hard for me to see the line that would go through those. That would be a good fit. Moderate is, I can kind of see it, but they're not going to be really close to that line. Strong is, man, are they really, really close to that line. Okay, and then lastly, we're looking at outliers. So for outliers, we're looking for any point that is deviating from the overall pattern. So in our case, if I was using this as an example, obviously a point over here would be an outlier, right? It is far away from the rest of its friends, so that would be an outlier, okay? So kind of the same general visual check as before. If it looks really far out there, it's probably an outlier. All right, so here's a basic like number line chart to give you a feeling for what types of words you should use and what numbers go with them. So I want you to notice a couple things about these numbers. The first thing I want you to notice is that the numbers stop at -1 on the low side, +1 on the high side. And we're going to talk about why that is in a little bit. Okay? So basically anything that is near a 0 has very little to no correlation to each other. In a scatter plot, these are numbers or points that are just all over the place. So once we start moving out from there, we start getting weak negative or weak positive, and that goes on until about 0.5 or so. And after about 0.5, we start calling it moderately negative or moderately positive, moderately strong in a negative or positive way. So that's from here to about here, from about 0.5s to about 0.8s. And then right above about a 0.8 or so, we start calling it strongly related to each other, okay? Strongly correlated, either as a negative or as a positive, either one, okay? All right, so we're going to talk about how we get those numbers in just a second. So first, let's talk about when we talk about positive association on a scatter plot, we're saying that those numbers, they basically go up over time, right? That you would see the numbers increasing, that the best fit line would look like a positive best fit line. All right, so two variables have a positive association when above average values of one tend to accompany above average ones of the other. So basically it's saying as x increases, y increases. Okay? A negative association would be as x increases, y decreases. Think about a line that goes downhill, right? As I move to the right, those y's come down some. Okay, so we have just given you these two examples. As x increases, y increases, so we have gone up this way, or as x increases, y decreases, so down this way. But there are more, right? There is also as x decreases, right? To make it a positive relationship, if I went this way instead, that would still be a positive slope line. So we could also say as x decreases, y also decreases. And as x decreases, y increases. So what do you notice about those? So in the positive association, the direction is the same for x and for y. If one goes up, the other one goes up. If one goes down, the other one goes down. So they are the same relationship, same direction. Okay? Whereas these have opposite directions. As one increases, the other one goes down. And it's got that opposing relationship going towards it. So this one would be opposite directions. Okay? So we're going to apply a number to this, like this type of graph, and we're going to give this type of graph a number of what we think its correlation number is. Okay, and we're going to make it fit on this number line somewhere and say what we think it is. Okay, all right, so correlation, that number is called R. It's the correlation number. This chapter is going to have a ton of R's, so make sure you're really clear on correlation is just the regular lowercase r. It is the value that measures the direction and the strength of the linear relationship between two numeric quantitative variables. Okay, so let's give you some facts about R's. We already know that they're always between -1 and 1. Anytime R is greater than 0, it indicates a positive association. Anytime R is less than 0, it indicates a negative association. Values near 0 indicate a very weak relationship for a linear relationship. The strength of a linear relationship increases or decreases as R moves away from 0 towards -1 or 1. Well, the strength would get stronger because we know that those most strong, going back to my diagram, those most strong numbers happen at the extreme edges of the graph. So if I am looking at the strength of the linear relationship does what as R moves away from 0, we would say it increases. Okay? And the extreme values, -1 and 1, only occur in the case of a perfect line. If every single point on that line, every single point on that graph falls right within a line, then that's going to have the extreme values of -1 or 1. All right, so I want to give you some visuals on this. So let's see if I can bring this into the graph. All right, here we go. So this is our graph for Rossmann-Schantz, and I'm having it do just 15 points at a time. In your notes paper, we're going to try to draw some that are really close to this. You'll notice that it won't have to be exactly for us to be able to get it. But first, I just want you to see a couple and see what some of these numbers look like. So it put a number out here. It put 15 dots out here. This definitely looks like a positive relationship, right? If I draw a line in it, it looks like it will go to the right and up. What do we think this correlation would be? Would it be closer to 0 or closer to 1? Okay, and then if you press check your guess, it says this is a 0.9. So on your notes somewhere, we have a 0.9. I want you to just sketch this general pattern on your notes under 0.9. Okay, so what I'm going to be doing here, let me move this. I'm going to be drawing a line that kind of looks like that and just kind of go, okay, there is some space in between these, but they don't wander too far away from that middle line. Okay, so I'm just kind of drawing just with dots, just kind of putting them in there so you can see what they look like. All right, so I'm going to hit reset. Let's see if we can get another one. So this is just random samples, so they're just going to just throw them out there. Ooh, look at that one. Okay, that is negative for sure, right? It's going downhill. All right, what do you think the number for this would be? Would it be closer to -1 or closer to 0? Let's go check. This is almost a -1. See how close they are for their lines and stuff? Really, the only places where it's not really working for us is like right here. like right there. I don't know if you can see it, but those three little dots that might make a triangle right there. Okay, so do we have anything that's really close? Hey, look at that, we do. Our last graph on our notes is a negative 0.99, so let's go ahead and sketch that one as well. And I'm noticing that I pretty much am just going to draw a line going downhill, and then I'm just going to put a couple of them out of that line a little bit. Okay, let's reset. New sample. Okay, what do you think about this one? Do you think this is going to be positive or negative? Negative, right? Because it's going downhill. All right, if you had to put a number on it, do you think this is closer to a -1 or closer to a 0? This one is a negative 0.87. Now we don't have a negative 0.87 on our notes page, so I'm going to go ahead. But notice to get an 87, they have to be pretty close together to kind of form that line. All right, what about this one? Positive or negative association? Negative, right? Okay, what do we think about this one? The other one was negative 0.8. What do you think this one is? Maybe a 0.7, a 0.6? Somewhere right around there. You have a negative 0.7. Let's go ahead and steal this picture for that drawing. So notice I'm showing a lot more of those dots are away from where I'm imagining that best fit line is. There's much more spread. Okay, so you've got 3 graphs on the bottom of your notes page for negative 0.7, positive 0.9, and negative 0.99. You should definitely see a difference between them about points that are closer together versus points that are far apart. All right, let's reset, see if we can get some more. So this is a positive point. Hey, we've got a positive 0.55. Let's use that one. So we'll use the positive 0.5 on our notes. We'll just kind of draw that in. Notice that these are, again, pretty far away from what we had before. And I can see that they generally goes uphill. Okay. All right, let's reset and do a couple more. So this one is going to be a negative, what do we think? Negative 0.5. We don't have one of those. Let's try it again. That's going to be a negative, what do we think? Is it going to be our negative 0.3? No, it's way stronger than that. Let's try again. This one still looks pretty strong, right? I don't think it's going to be a negative 3 either. This is a negative 9. How about that one? Wow. I'm not even sure I can see a line for that one. Is that even positive or negative? What do you think? This is what a 0 looks like, where you're like, I don't know, it could go either way. So in a 0, it just looks like a big cloud of points that could be connected to go down, downwards, upwards, vertical, horizontal. It's like you could kind of put a line through any of those. Okay, so let's draw that onto our notes page for r equals 0. So the last one we're looking for is we're looking for a negative 0.3. Let's see if we can get one. This is a positive 0.1. That's too strong. Negative, negative, negative. Let's check this one. We'll take that one. Oh, we're looking for a negative, darn it, negative 0.3. All right, let's keep looking. What do you think that one is? Yeah, negative 0.1, barely downhill. What about this one? Yeah, it's kind of hard to see here too, right? The general trend is kind of upwards, I guess. Positive 0.4. You think that one's going to be a negative 3, or you think it's going to be stronger? Yeah, way stronger. Way strong. Again, negative 0.8. What about this one? Again, that's a negative 0. So a negative 0.3. There we go. Now take a look at that for a second. Doesn't it just look like a cloud like a 0 does? So we really don't see a definite pattern for something until you're right around 0.5 or more extreme than that. I'm going to go ahead and draw this one, but there is a trend. If you kind of like let your eyes kind of run out of focus, you can see that generally this is going downhill. So I'm trying to represent that on my graph. So I put a few that are kind of going downhill, and then I spread them out a little bit and hope that that works. Okay. All right, so here's what my graph looks like on my notes. Right? Notice that a 0 and a 0.3 don't look that significantly different. A 0.5 and a 0.7 are kind of in the same neighborhood. That's why they're moderate. And then we've got strong, where you can definitely see those lines going on. All right? All right, so there's our general idea of a correlation number. So the next one is, what if we had to go and calculate it? Well, this is not a fun deal at all, okay? And it is a bit complex to see what correlation is, but in practice, you should use your calculator or software to find R because it is so tedious. And in this chapter, we're going to start showing you how to use calculators using our TI-84s. I'm going to be putting some videos on. Some of them will be with me, some of them will be other ones that I found online about how to do individual things for these. But I thought we'd just give you the general idea for this one. Notice that the calculation, so I want you to see a couple things in this calculation, okay? I want you to notice that the formula itself, if I look at this first formula, includes taking every x value and figuring out how far it is from the mean. And this one is not being squared, so we want to keep track of positive and negatives. And then it's divided by its spread. What else does that? Takes a point, subtracts it from the mean, and divides it by its spread. Isn't this the z-score for x's? So this is the z-score for x. And then what about this one? It's the z-score for y. And then we're going to multiply them together. So if they're both positive z-scores, if the x and the y are both positive, then we are basically saying that they are both above average, right? And that should add into our correlation number. Now, if I have a whole bunch of those where I'm getting positives, then it's going to add to my R number for the end, because the next thing is I'm going to do it again. And here's another z-score for y and another z-score for y, and we're just going to keep doing that over and over. So if they're both positive, I'm adding to the R value. If one of them's positive and one of them's negative, so let me go put the colors in here for a second. If the z-score for x is positive and the z-score for y is positive, and you multiply them, you'll get a positive. Okay? Obviously. What if the z-score for x is negative and the z-score for y is positive? Well, when you multiply them, you're going to get negative. And what happens if the z-score for x is negative and the z-score for y is negative as well? We also get positive values. So it's kind of balancing out how many are above the average, how many are below the average, and we just keep taking those products, multiplying them together and adding them together. Once we get that final sum, we average it out, and minus 1 is the spaces in between those numbers. So if I had 4 numbers, I would divide by 3 at the end, after I've added up all of those z-score combos, all those z-score products. Okay, but there is an easier way to do this on our calculator, and we will show you that very soon. So start bringing your calculators for Chapter 3. We definitely want to do those in class or for videos for homework. All right, some last facts about correlation is there is no distinction in a correlation number between x and y. Since you're going to multiply them anyway together, it really doesn't matter for correlation. Now for a graph it does matter, but when I'm just calculating the correlation number, right, it doesn't really matter whether it's an x or a y to calculate it. Okay? R does not change when we change units. So R is not like this is my number 0.9 feet or negative 0.35 miles per hour. There are no units. It's just R is -9, R is 0.34, or sorry, R is negative 0.9, or R is 0.3, okay? And R has no unit of measure, okay? We are not using any units for these at all. All right. And then a few things to be careful of when you're calculating correlation. Remember that in order for you to calculate correlation, both variables have to be numbers themselves. Okay, so that means that they have to be quantitative as well. Okay. Also, correlation does not describe, what did I write here? Correlation does not describe blank relationships between variables, no matter how strong the relationship is. Correlation does not describe non-linear. So correlation is not meant to use with curves. It's meant to be a best fit line number. Okay, so then the question is correlation resistant or not? Is it stuck and less likely to move? Well, it is strongly affected by outliers, right? Because up here, if I'm finding a z-score, if it's really far away, it's going to add a lot to that R number. Okay, so it is strongly affected. That means it is not stuck. It moves a lot. Okay, and then also keep in mind, this is just one measure of looking at two different variable data. It is not the end all to tell us absolutely everything about our data set. So correlation is not a complete summary of the two variables of data. Okay. All right, so that is it for today. We will see you later. Bye.